Welcome to our class on basic electronic circuits. The topic for today is working and construction of metal oxide semiconductor field effect transistor, that is MOSFET. So let's begin with classification of field effect transistors. Field effect transistors are the transistors whose current is controlled by applying an electric field at the input. Field effect transistors, that is FET, can be broadly classified into two types: junction field effect transistor, that is JFET, and metal oxide semiconductor field effect transistor, that is MOSFET. MOSFETs are further classified into depletion and enhancement mode. Both depletion and enhancement mode have two types, P-type and N-type. So you have P-channel MOSFET, N-channel MOSFET for both depletion and enhancement. Let's start off with the construction of depletion MOSFET. So we start off with a simple wafer that is going to be a P-type if I'm talking about an NMOS, and I'm going to have active regions, that is source and drain. When I have a depletion MOSFET is connected, the source and drain regions are connected using a channel. The channel is also called as implant. It is of the same type of doping that is used for source and drain. If it's an NMOS, it's going to be N-type. Then just above the channel you have an oxide layer. The oxide layer is then topped up with a metal gate. So you have basically four electrodes. You have source, gate, drain and substrate. The material used are P-type for my substrate, N-type for my source, drain and my channel. The gate is formed using silicon dioxide topped up with a metal gate. Now let's talk about the construction of enhancement MOSFET. The construction is very similar. You start off with a wafer, that is substrate. When you're doing an NMOS, you're going to start off with a P substrate. You will have active regions which are going to be made of N plus region. The difference is I don't have an implanted channel here. Instead, in the channel region, you directly have a silicon dioxide that is topped up with a metal gate. So basically, I have four layers here: P-type, N-type, source and drain, silicon dioxide topped up with a metal. So I have four electrodes even in this case. There are source, gate, drain and substrate. Now let's talk about the depletion MOSFET working. We'll be mainly discussing an N-type MOSFET. So the construction remains the same. Now I'll be talking about the working. So it will be dependent more upon the field that I apply at the input. The input is nothing but at the gate. So when I apply a positive gate voltage, more number of electrons from the substrate will be attracted towards the implanted channel and the channel will increase. This channel helps you to have connection between source and drain and allows the charge carriers to flow in. Since the active regions are going to be made up of an N-type and an NMOS, you will have electrons traveling between source and drain, and the current is going to be constituted from drain to source. Let's see what happens when you apply a negative voltage or a voltage that is less than the threshold voltage required to turn on the MOS. When that happens, you will have more number of holes gathering up at the silicon dioxide interface. That is, the channel will now be overtaken by the holes. In this case, there will be no current flow or very little current flow because you will have the holes taking up the channel, so there will be no proper path for conduction for electrons to move from source to drain. This region of operation is called as accumulation mode. Now let's see when you apply a negative voltage which is very close to 0 volts or which is little greater than threshold. When you do that, you still have little number of charge carriers, that are electrons, lining up just very close to the implant, and you still have a channel formed between source and drain. There is still a channel present even if the electrons do not come up near the implant, and hence you will have conduction. So when I have a depletion mode MOSFET, I still have conduction for a little negative voltage, and there is no depletion mode in my depletion MOSFET. So basically my depletion MOSFET, which is an N-type that I am discussing here, is going to conduct for both positive voltage as well as negative voltage. Of course, the current will go on reducing as your VG becomes more and more negative. Now let's look into the working of an enhancement MOSFET. When I have enhancement MOSFET, I'll be again applying all three types of gate voltages and I'll observe what is happening with the device. So when I apply a positive voltage, I'll see the electrons being attracted at the silicon and silicon dioxide interface, and that will help me form a channel between source and drain. This channel goes on increasing as you increase the gate voltage. Since you have negative charge carriers building up in the channel, this mode is going to be called as inversion mode. As VGS increases, my current ID will also increase because the width of the channel will increase. So the number of charge carriers that will move from source to drain will also increase. When you apply a negative voltage, now you will have holes or a majority charge carriers in the p-type substrate building up at the silicon-silicon dioxide interface. So in this case, you will have accumulation of charge carriers, but there will be no current flow. So this is going to be a mode of operation where there is going to be no current flow when you apply gate voltage that is negative. Let's see when you apply a gate voltage which is very close to 0 volts or which is little less than VTH. When that happens, you don't have any free charge carriers building up in the channel. The channel in this case is going to be occupied by your immobile ions, and hence this region is going to be, this mode is going to be called as depletion mode, and there will be no current flow in this case. So your enhancement mode MOSFET will only conduct when it has a positive voltage applied in case of an NMOS. For all other voltages, it will not conduct. The MOSFET in fact starts conducting only when your VG voltage applied is greater than the threshold voltage. Now let's move on and talk about the MOSFET symbols. So since there are two devices, depletion and enhancement, there are two different symbols. The ones that are shown here are for depletion MOSFET, N channel and P channel. Now the one that is shown here is the model that is used, the symbol that is used for my enhancement. If you see there's a difference between the symbol. The difference is, in this case, the source, drain and channel are separated as compared to the one that I had shown earlier, which was my depletion. Here, as you can see, when you apply a gate voltage, you will have, and a drain voltage is positive, you will have the entire device conducting. When there is no gate voltage applied, there is no current flow. This is an N-channel MOSFET. The one on the right side, the one that I've drawn, is a P-channel MOSFET. Right? The arrow in here indicates the formation of PN junction in the wafer, that is very close to my silicon dioxide interface. Let's move ahead and talk about the characteristics of an N-channel MOSFET for a depletion mode or a depletion MOSFET. Now you can see there are two characteristics. We have a transfer characteristic and your output characteristics. Transfer characteristics is when you plot your input voltage, that is VGS, with respect and observe the change in ID. Output characteristics is the one that is plotted on my left hand side, and that is going to be variation in ID with respect to the change in my output voltage VDS. If I draw slope for both of them, I'll get my characteristic equations for GM and RO that are found by just drawing the slope. When I talk about my output characteristics, I have three regions of operation: ohmic, that is nothing but linear, saturation and cutoff. There is a small line that differentiates ohmic and saturation, that is when my VDS is equal to VGS. The moment VDS becomes greater than VGS minus VTH, you enter into saturation. And when VDS is less than equal to VGS minus VTH, that is when you are in the linear or ohmic region. You have cutoff when VGS is less than VTH. Let's move ahead and also see the characteristic equations for the depletion N MOSFET. Now the first one gives you ID in both ohmic and linear region. The simple explanation for that equation is ID is equal to VDS by R, general equation. I know my definition for R, that is resistance, is equal to resistivity into L by A, right? And I know resistance is nothing but reciprocal to my conductance G. So I can write ID is equal to G into VDS. G is nothing but conductance. And G can be written as conductivity into A by L. That is how we got back to that first equation, which is ID is equal to area, which is B into W, that is your breadth into width, upon length L, into conductivity, which is given by electron charge into my doping density into my mobility mu n, into, when I apply it with my multiply it with my VDS, I get my current ID. Then let's look into the second equation. The second equation is for a saturation region. It is same as my JFET equation. It does follow a parabolic curve and hence it follows my Shockley's equation. The other parameters are GM and RO that you can derive from your characteristics. You have intrinsic gain mu, which is given as GM into RO. You can also find out GM and GMO if you know VGS and VP and IDS as well. Let's now talk about the enhancement NMOS characteristics. So on my right is my transfer characteristics and on my left is my output characteristics. So the point that has been shown with arrow on my VGS versus ID characteristics is my VTH point. Only when my VGS is greater than my VTH, my MOSFET starts conducting and I have a current ID flowing. If I draw slope for both of them, I get GM and RO. The more of the point of separation for ohmic and saturation region remains the same even in an enhancement MOSFET. Let me now talk about the characteristics equation for an enhancement MOSFET. So for an enhancement MOSFET, ID is equal to Kn twice VGS minus VTH, VDS minus VDS the whole square, which is for ohmic or linear region. For saturation region, it is given as Kn VGS minus VTH the whole square. Since it's a discrete device, we are not talking about the channel length modulation parameter here. Then we have Kn is equal to half mu n Cox into W by L, or I can also have another device parameter which is Kn dash is equal to mu n Cox. And let's take a simple Q&A on MOSFET that helps you understand the depletion MOSFET. Okay, so if you go here, it's a very simple question. It says for a depletion MOSFET, VGS is equal to 3 volts, IDS is equal to 5 volts, ID is equal to 2 amperes. You just have to find out the pinch off voltage. So for that, you will be referring the Shockley's equation, and it will help you to find out your VP value, which comes out to be 8.6 volts. Let's look into the next question. The next question is for an enhancement MOSFET, VTH is equal to 0.7 volts, VGS is equal to 3 volts, VDS is equal to 5 volts. You have to determine the region of operation for NMOS. It's simple to find out that it is saturation because I know once VDS is greater than VGS minus VTH, it enters into saturation. Let's look on the next question. It says for an enhancement PMOSFET, applied gate voltage is minus 3 volts and the threshold voltage is minus 1.5. You have to find out the voltage after which the PMOS enters into ohmic region. So I'm going to use the same relation, that is VDS is equal to VGS minus VTH at the edge of my saturation. So that gives me for VDS less than minus 1.5 volts, my PMOS will enter in the ohmic region. These are quick equations for you to solve these 3 questions. Let's go ahead and look at few more questions on MOSFET. The first one says that the MOSFET operation in saturation, Kn is equal to 0.1 milliamperes per volt square, Vt is equal to 1 volt and Vgs is equal to 3 volts and Vds is equal to 5 volts. Lambda is given to be 0, so you have to determine value Id. So in this case, Id comes out to be 0.4 volts. Next, let's look at the characteristics that they have provided. Now you have to tell me which device is this and which characteristics it is. It's a PMOS device and the characteristics are output characteristics. There are quick equations given and explanation given for you to understand these questions. Thank you.